Welcome everyone to the General IC Colloquium. It's my great honor and pleasure to introduce Professor Ellen Zweibel to you today. Ellen studied mathematics at University of Chicago. Then she got her graduate studies at University of Princeton. After that, she spent many years at University of Colorado in Boulder, where her primary field of research became plasma astrophysics. That is, she's still working on today. Since 2003, she is a William Kraushaar Professor of Physics and Astronomy at University of Wisconsin-Madison, and in 2016 she got the Maxwell's Prize for Plasma Physics. That is her main field of research. Today she will give us a talk, the basis of the cosmic ray feedback written on the wind. Ellen, please.
Thanks everybody. I'd like to begin by thanking everyone for a really interesting and wonderful week. Nicola, you've been a great host. So I'd also like to say, please interrupt me at any time if you have questions. Okay. So I'd also like to acknowledge my collaborators. So the people whose names are in green are students and postdocs who will need graduate schools in some cases, jobs, etc. And without them, I really couldn't have done all of this work. So feedback is the observationally motivated and theoretically motivated idea that star formation and the growth of supermassive black holes and galaxies are somehow self-limiting. And the cycle might go something like this. So stars form from dense gas, and some fraction of them release their energy at the ends of their lives in supernova explosions. And the energy and momentum from supernova explosions somehow drives winds, shown here in M82, and in some way this disrupts the star formation cycle. And cosmic rays are the relativistic component of interstellar matter. They're very minuscule in number, 10 to the minus 9 by number, but they have, excuse me? Yes, all right. Well, I'll try, but I have to get over and advance my slides. So here's an image of a star-forming galaxy M51. The color represents brightness. The little line segments represent the orientation of the magnetic field. And this is imaged in synchrotron radiation, the signature of cosmic ray electrons. And here is a signature of cosmic ray nuclei, shown superimposed on a CO map. Okay. So what could cosmic rays do for feedback? So let's just imagine that a relativistic fluid, which we'll later take to be cosmic rays, is providing some of the pressure in a galaxy. And here's a comparison of what that relativistic equation of state does in driving an outflow versus an ordinary gamma equals 5/3 gas. So the dashed lines represent sound speed, and the solid lines represent the fluid speed, and you can see that you drive a faster wind with a gamma equals 4/3 gas. This is some work by Corey Cotter, an undergraduate student in my group, and Chad Bustard, a graduate student. So cosmic rays are able to deliver energy and momentum in a more sustained push, and they drive a faster wind. We'll later see that they also drive a lighter wind. But this is just an assumption that we can treat cosmic rays as a fluid. So what would it take to make this fluid approximation? Well, it's a very, very multi-scale problem. So in galaxies, we're interested in kiloparsec scales, and cosmic rays at the average energy have a gyro radius in the galactic magnetic field that's considerably less than 1 astronomical unit. Now, that in itself doesn't necessarily bother us. We work with gases all the time that have mean-free paths that are short. compared to the size of the system, but cosmic rays are collisionless and non-Maxwellian. So our job in seeing how the energy and momentum of cosmic rays could be harnessed is to develop some sort of fluid theory to treat them, because a full kinetic theory over this many orders of magnitude is pretty hopeless. So the plan of this talk is I'll tell you a little bit about the properties of cosmic rays that are important for this problem. Then I'll show you that the cosmic ray treatment, how we treat cosmic rays, actually matters for the answer. And then I'll go a little bit into the theory of what we can call cosmic ray hydrodynamics, a fluid theory for cosmic rays. I'll show you what the foundations of that are in plasma physics, and then we'll go through some applications, some of which have observational consequences, and others are a little more speculative, a little less firmly pinned. Okay, so the cosmic ray energy spectrum looks like this. I like this figure because it shows you how many different experiments go into making up this spectrum, which, as you can see, extends over 12 orders of magnitude in energy. And I'd also like to give you some idea of what the fluxes are at these energies. So at this so-called knee of the cosmic ray distribution, at a few PeV, there's 1 per meter squared per year, the flux reaching the Earth, but the ultra-high energy cosmic rays, 1 per meter squared per 100 years. And the GeV cosmic rays, which form the bulk of the energy density, are much more common. So these ultra-high energy cosmic rays, they're probably extragalactic in origin, they're still mysterious, they're very interesting, but I'm going to be focusing on the mildly relativistic protons that provide most of the pressure and most of the energy density in galactic cosmic rays. So the composition of cosmic rays is actually very close to solar system abundances, with the notable exception of the very light elements, lithium, beryllium, and boron. And that's interpreted as a signature of spallation, that carbon, nitrogen, and oxygen nuclei have passed through something like 3 to 5 grams per square centimeter of matter from when they were accelerated to when we detect them. And you can translate that into a confinement time at a GeV of about 20 million years. There's also a notable lack of the so-called R process elements, the elements formed in supernova nucleosynthesis, and this suggests that cosmic rays may be energized by supernova energy, but they're not themselves supernova ejecta, that they're accelerated from the interstellar medium, have a basically interstellar composition. Another important clue about cosmic rays is that they arrive at the Earth in a very isotropic manner. So this is the amplitude of the anisotropy as a function of energy below about 1 TeV. They're too strongly modulated by the solar wind to get a real check of how they're coming in from the galaxy. The anisotropy increases with energy, but even in this range, it's really quite small. Recently, some anisotropies at a very low level have been discovered at the very high energies, and this may be an important clue to the origin of these particles, and maybe a signal that the fluid approximation is breaking down. There's a strong similarity in the behavior of cosmic rays across many galaxies. So this is a plot of the so-called far infrared radio correlation. So the far infrared flux from a galaxy is a signature of its star formation rate, and the radioluminosity at this frequency is synchrotron radiation. It's a measure of cosmic ray and magnetic energy density. And the strong correlation of these quantities for many galaxy types and across many orders of magnitude in luminosity really hints at some kind of self-regulation process that maybe stretching it a bit, but maybe it's evidence for feedback. Okay, so if we distill these facts and a few more, we can summarize the properties of cosmic rays as follows. So they're accelerated from the interstellar medium in one-time events. And we know that it's one-time events versus a continuous acceleration process, because if cosmic rays were continuously accelerated in the interstellar medium, we would expect the oldest cosmic rays with the most spallation products to be the most energetic. But actually, the most energetic cosmic rays are the youngest. So that's evidence for a one-time acceleration origin. At 1 GeV, they're confined to the Milky Way for about 20 million years, and they're scattered in the galactic magnetic field with a mean-free path of order 1 parsec that also increases with energy. And you can keep the galactic cosmic ray pool in a steady state with about 10% of the non-neutrino energy from supernova explosions. Okay, so there are two types of cosmic ray interaction with the environment. They interact as single particles, and that's how we get radiation from them. The synchrotron, the inverse Compton, and the Bremsstrahlung from electrons. The gamma rays from pi naught decay, neutrinos, electrons, positrons, light elements. These come from ion cosmic rays. And at lower energies, at MeV energies, they're also an important source of ionization and heating in the interstellar medium. So these collisional interactions are very important. We wouldn't really know much about cosmic rays without them, but in this talk I'll be focusing on the collective interactions. So on microscales, cosmic rays drive instabilities, which transfer energy and momentum to the fluid. Through this process, they affect the structure of collisionless shocks, and they influence the macroscales as well through the dynamics of interstellar and intracluster gas. But before leaving collisionality, I want to show you one example of what we can do with it. So this is based on the PhD thesis work of my former student, Tove Joost Hull, and my colleague, Jay Gallagher. And we decided to look at this sort of tenet, well-accepted tenet for the galaxy, that magnetic fields and cosmic rays are in energy equipartition. So here on the left is a plot of cosmic ray energy density versus magnetic energy density. And you can see that for the Milky Way, M31, very much like the Milky Way, and a Large Magellanic Cloud, equipartition is a good assumption. Then as we go to starburst galaxies, M82 and NGC 253, which have much higher energy densities of everything, the cosmic rays start to peel away from equipartition. Their magnetic fields, magnetic energy densities are stronger than their cosmic ray energy densities. And when we go to ARP 220, which is a pair of merging galaxies, which is a tremendously luminous infrared source with an enormous star formation rate and very, very high densities of everything, the cosmic rays are way, way down from equipartition, and the magnetic fields are way up. So how can we explain that? Well, if we order these galaxies now by ratio of magnetic to cosmic ray energy density versus gas density, we can see a pattern. This blue line actually represents a theoretical prediction by Elliot Quattert and his co-workers. And so we think that the deficit of cosmic rays in systems like ARP 220 and to a smaller extent in starburst galaxies is due to the very high energy loss rates. Okay, so now let's go to the plasma physics of cosmic rays, and let's begin by assuming that cosmic rays behave like a fluid on scales greater than the mean free path lambda, which is about a parsec, which is very small on galactic scales. So let's assume that they're a gamma equals whatever fluid coupled to the thermal gas, and we're going to look at three different cases. So the relativistic limit, gamma equals 4/3. The case in which they're uncoupled, just zipping around, in which case they behave like a gamma equals 0 fluid, and then a sort of intermediate case, gamma equals 1, which is maybe a crude representation of diffusion. Okay, so we saw a little bit already with cosmic ray-driven winds, and what I'm going to tell you now is something about the equilibrium and stability of the interstellar medium. So this is addressed by work by one of my current students, Aaron Boettcher, also with Jay Gallagher and Bob Benjamin, and this is a study of the edge-on galaxy NGC 891. So there's a layer of ionized gas about a kiloparsec thick, half thickness of about 1 kiloparsec. And the question is, what supports this gas perpendicular to the plane of the galaxy in the galactic gravitational field? So here's a plot of pressure gradient versus gravity that is necessary or exists to support the gas. So the black is what the pressure gradient has to be to maintain equilibrium. And here are some different components. So here's thermal pressure, and you can see that the thermal pressure gradient is just way too weak to hold up this gas. And if you add turbulent pressure, that helps. And if you put in magnetic and cosmic ray pressure from synchrotron measurements, and you add them all up, it works. No component alone can do it, but with magnetic fields and cosmic rays, you can hold this gas up perpendicular to the plane of the galaxy. So this is good. But the next question is this system stable? And in particular, is it stable to the so-called Parker instability, which was developed by Parker in 1965. And so schematically, the Parker instability works like this. Here's the galactic plane, which exerts a gravitational force. And there's a magnetic field parallel to the plane. And the magnetic field and some cosmic rays, which are not shown here, are holding up some clouds in gravitational equilibrium. Now, if we make an undulate perturbation of this magnetic field, the gas can fall down, can fall toward the galactic plane, and the magnetic field and cosmic rays can expand away. So that's the essence of the Parker instability. The free energy in the system is the gravitational potential energy of gas that's held above its natural scale height by magnetic fields and cosmic rays. And the stabilizing force is the compressibility of the gas. So as the gas flows toward the galactic plane, it gets compressed, and you have to do work to compress it. And to the extent that cosmic rays are coupled to the gas, you have to do work on the cosmic rays to compress them also. Now, Parker, this work on the coupling was done in the late 1960s, and Parker did his work in the mid-1960s. So his work predated the fluid theory of cosmic rays, and he assumed that gamma cosmic ray equals 0, and so he obtained a harsher and more stringent criterion for stability. But we put cosmic rays back, and here's what they do for NGC 891. So, as usual with extragalactic systems, we don't know everything, and so the stability diagram is plotted versus a couple of unknown parameters. Here on the x-axis is the magnetic scale height, and as you make the magnetic scale height larger and larger, the magnetic field becomes less and less important in holding up the gas, and the system becomes more stable. Here is the so-called filling factor of the gas that we detect, and the larger this filling factor is, the lower the mean density of the gas is, and the smaller the gravitational force is. And we also don't know, actually, we only know the projected radius of the gas. We don't know where it actually is, and that accounts for the discrete nature of this diagram. So if we assume that cosmic rays are decoupled from the gas, gamma cosmic ray equals 0, none of the equilibrium configurations are stable. It's just got to be unstable. If we make gamma cosmic ray equal 1, then systems with relatively large magnetic scale heights become stable. And if we make gamma cosmic ray 4/3, then we get these green solutions with smaller magnetic scale heights. And if we make gamma cosmic ray 145, which accounts for the only partially relativistic nature of the lowest energy particles, we get a few more solutions. So the stability of these models of the gas layer that are held up by magnetic fields and cosmic rays really depends on what the cosmic ray physics is. Are they coupled to the gas or not? And so the story with cosmic rays is kind of complicated. They have two kind of opposing influences. They help support the gas, but they're a naturally buoyant fluid, which is kind of destabilizing, but their compressibility can stabilize the system, or their equation of state more generally. Okay, so I hope that motivates you to go through this fluid theory. So the perpendicular dynamics are actually easy. So cosmic rays are held up perpendicular to the magnetic field by their current, their collective Lorentz force. And the Lorentz force on the thermal gas is the same, their current crossed with the magnetic field. Now, of course, we don't actually know what the current in the gas is or what the current in the cosmic rays is. Those things cannot be measured, but we do know that their sum is related to the magnetic field through Ampere's law. So if we add the cosmic ray and gas momentum equations together, we get a simple balance equation. The Lorentz force on the thermal gas is the Lorentz force on the total system minus the perpendicular gradient of the cosmic ray pressure. So this looks like sort of a sleight of hand, but it shows how the cosmic ray pressure gradient can influence the force on the thermal gas through this magnetically mediated momentum transfer. The parallel dynamics are a little more subtle. And to explain those, we have to go into the concept of gyro-resonant scattering. So here's a magnetic field line in red, and this magnetic field line has structure on two scales. It has a very large scale structure and a kind of wiggly structure. And here in black is the gyro orbit of a cosmic ray. And the gyro radius of this cosmic ray is kind of intermediate between the large scale and the tiny scale. So this is kind of like riding your bike. So you go up and down the hills, your bike stays on the hills, and if the road surface is kind of rough and poorly maintained, your hands will vibrate a little bit, but you can stay on your bike. But if you come to a trench in the road which is about the width of your bicycle, you will interact very strongly with that trench. And that is basically gyro-resonant scattering, which is expressed mathematically as the condition that the Doppler shifted frequency of a wave that a cosmic ray sees as it travels along a field line is equal to its gyro frequency. In that case, it's like a resonantly driven harmonic oscillator, and it undergoes a very strong interaction with the magnetic field and scatters to another field line. And we can estimate the diffusion coefficient from this process. So there's an amplitude, delta B, of the fluctuation, and the field line, that fluctuation makes an angle, delta theta of delta B over B. And if we assume that the particles undergo scattering with an RMS of delta theta squared, which is this, and with a frequency which is equal to the gyro frequency, we come up with a scattering frequency of the gyro frequency times delta B over B squared. And this is, to within a factor of order 1, the same scattering frequency that you get from a much more complicated calculation. If we interpret these fluctuations as hydromagnetic waves traveling at the Alfvén speed, then since the Alfvén speed is much less than the speed of light, there's very little energy exchanged in this scattering, just momentum, or almost entirely momentum. Okay, so at this point, the subject bifurcates. So there are two versions. One version is that the waves that the cosmic rays scatter from are generated by the cosmic rays themselves, by a mechanism that I'll tell you about, and that's the so-called self-confinement picture. And it leads to what I like to call classical cosmic ray hydrodynamics, a theory that was developed in the 1980s. But there's an alternative point of view, which is that the waves are just there. They're part of a turbulent cascade in the interstellar medium. So in this extrinsic turbulence picture, it turns out that we can also develop a fluid theory, which I call generalized cosmic ray hydrodynamics. And I'll talk first about this and then about this. And I'll show you again that the treatment really matters. Okay, so cosmic rays can feed energy and momentum to Alfvén waves through this gyro resonance. And I'll just schematically show you all the ingredients. This is the growth rate, gamma CR. This delta function is the resonance condition, shows that only resonance scattering is important. This is the momentum derivative of the cosmic ray distribution function, and it's negative. The number of cosmic rays decreases with increasing momentum, and that tends to damp the wave. But anisotropy, more cosmic rays going in one direction than the other, leads to growth of the waves. And fortunately, you can write this sort of nasty expression in a much simpler way. The growth rate of the streaming instability is the ion gyro frequency, which is very large, times the ratio of cosmic ray to ion number density, which is typically very small, about 10 to the minus 9 in the interstellar medium, times the mean drift velocity of the cosmic rays divided by the Alfvén speed in the plasma minus 1. So this is positive if cosmic rays are streaming faster than the Alfvén speed. And this is called the streaming instability. It was discovered in the late 1960s by Russell Kulsrud and others. So the cosmic rays react back on the waves, and that's described by a so-called Fokker-Planck equation. And I've written it down. So these E1 and B1 are the fields in the waves, and F0 is the equilibrium cosmic ray distribution function, and F1 is the change in the distribution function caused by E1 and B1. And amazingly, if you actually evaluate this expression, it has the form of a diffusion equation in momentum space. And the largest component of that diffusion tensor is the scattering component. The energy change is relatively small. And if we multiply the Fokker-Planck equation by particle energy and integrate over momentum space, we get an energy equation. And it says that the rate of change of cosmic ray energy density plus the divergence of cosmic ray energy flux is equal to the rate at which cosmic rays transfer energy to the waves. Which makes sense, but it's not terribly useful because we don't know what the intensity spectrum of the waves is, and this is a sort of nasty expression. But if we make the assumption, which is justified by the isotropy of cosmic rays that we see, that cosmic rays are actually well scattered by the waves and have a short mean free path, we can make this equation a lot more useful. And it turns out that we can write the right-hand side in this much simpler and intuitive looking form, that the change in cosmic ray energy is the Alfvén speed dotted with the gradient of cosmic ray pressure. And we can think of this as a sort of frictional heating, that cosmic rays are streaming down their pressure gradient at the Alfvén speed relative to the thermal gas, And that is frictionally transferring energy from cosmic rays to gas. So this can all be done. We can go a little further. Did I just change some connection thing? Yes, no, okay. We can go a little bit further. We can write down equations for the waves, and they're affected by changes in the background and driving by cosmic rays and dissipation, and we can identify the dissipation with heating of the thermal gas. So the microscopic picture all makes sense. And this is the core of this fluid treatment. So it was developed in the 1980s by Heinz Folk and his collaborators. They were interested in how cosmic rays modify interstellar shocks. The key ingredients are that cosmic rays stream down their pressure gradient at the alphane speed relative to their thermal gas. They transfer momentum through that pressure gradient. They heat the gas at this rate VA.grad PC. They can also diffuse a bit. You can calculate the diffusivity. And this has been applied to shocks, the original intention, to galactic winds, to heating the interstellar medium, and to heating the intracluster medium in galaxy clusters. And now I'll show you some of these applications. So here is some work we did a number of years ago on a model for a wind from the Milky Way. And this was developed to explain the soft X-ray emission from the inner galaxy. So this is a map made by ROSAT of the 3/4 kilovolt surface brightness. The northern hemisphere is actually strongly modified by local features, so we concentrated on the southern hemisphere. This had previously been modeled as kind of a static ball of hot gas in the inner galaxy, but you can actually get a better fit to the observations with a wind model. So we used a model that had been developed by Breitschwert and other collaborators of Heinz Folk. It's a very simple model. There's a vertical magnetic field that flares. Gas and cosmic rays stream out along those field lines. Because it's a simple model, we can run it tens of thousands of times, and that's what went into making this plot, which is cosmic ray pressure at the galactic plane, gas pressure at the galactic plane. The color represents mass loss rate in solar masses per year. The best fit is here, so about equal gas and cosmic rays. So this is a chi-squared with the X-ray data versus synthetic X-ray data. And these hyperbolae represent lines of constant total gas plus cosmic ray pressure. If the pressure is too low, the gas falls back. You can't drive a wind. If the pressure is high enough, the gas just comes boiling out of the galactic plane. It never goes through a critical point, passing from subsonic to supersonic. And the colored solutions are sort of bona fide wind solutions. If you follow one of these hyperbolae of constant pressure, say this green one, it starts green and it ends up blue. And so what this says is that winds that are dominated by cosmic rays carry less mass at a given pressure than winds that are dominated by thermal gas. So the cosmic rays have a dual role in the wind. They supply pressure. They drive the gas out by their pressure gradient, but they also heat the gas. And so here's a comparison of gas temperatures with and without cosmic ray heating. Red is without, the gas just cools adiabatically. Blue goes close to red for a while, then as the flux tube flares out, you get a burst of heating as the cosmic ray pressure gradient gets large, then again, everything adiabatically cools. So cosmic ray driven winds are hotter than thermally driven winds and have less cooling. So galactic winds are notoriously multi-phase. You have gas of many different temperatures in them. And so we decided to look at what cosmic rays do to clouds that are cooler than the ambient medium. So this is just a simple test problem. Here's a cosmic ray source shown schematically. Magnetic field lines from the source pass through a cloud, which is immersed in a hot medium in pressure equilibrium. And let's see what the cosmic rays do. So this is work by Josh Wiener, a postdoc in my group. Okay, so Josh was the first person to demonstrate the so-called bottleneck effect, which was predicted back in the early 1970s by John Skilling. So here's a comparison of what happens with and without the cloud. So we turn on the source and without the cloud, and a cosmic ray front goes out, and you can trace what it does over time. And by 6 million years, which is a couple of Alfvén crossing times, it's established kind of a steady pressure gradient in which the cosmic ray density goes up or goes down as the Alfvén speed goes up. The Alfvén speed goes up because the density is going down in this model. And it converges to a steady state with a constant product of cosmic ray energy density times the Alfvén speed. I don't know if you can read this, but it's the gamma cosmic ray index. Okay. If we put a cloud in, so now we're just holding the cloud in place, making a density maximum, there's an Alfvén speed minimum, and what happens, instead of establishing a steady pressure gradient, is that the cosmic ray pressure profile flattens between the source and the density maximum, and then the cosmic rays experience a plunge in their pressure and then a smoother gradient. Why does this happen? It happens because this behavior predicts that as the Alfvén speed goes down, the cosmic ray pressure goes up. So the cosmic ray pressure would actually go up as you go toward the maximum in the source, but that means that the anisotropy goes the other way. So instead of exciting waves by streaming away from the source, they would want to excite waves streaming towards the source. And what they do instead is they seek an equilibrium of just a flat profile, no waves, no engagement with the gas. As they come to the end of the region where the Alfvén speed is going down, they re-engage, the streaming physics works again, and we see this plunge. So what does that do? What does that do to a cloud? Now we're going to unfix the cloud and let it respond to cosmic ray pressure and energy deposition. So here is the cosmic ray energy density when the gas is allowed to respond. Here's the initial density profile, and here is the density profile at subsequent times. And you can see that the cloud is being progressively eroded. The density maximum is moving backwards. And this is happening because that big plunge in cosmic ray pressure delivers a huge surge of heating that evaporates the cloud. But if there's strong radiative cooling of the cloud stays together, and the cosmic ray pressure gradient just moves it forward. So the cloud is actually being accelerated. I wondered whether these bumps here are just numerical noise, but they're actually reproducible features that represent waves bouncing back and forth inside the cloud. So this gives us hope that we can maybe explain multi-phase galactic winds as a product of cosmic ray acceleration. If we zoom in on these fronts that are the interface on the far side of the cosmic rays and the cloud and the hot gas, we get these thin fronts. Look at this scale now. This is fractions of a parsec, in which the temperature goes up over a relatively short distance. The cosmic ray pressure goes down, and the gas pressure goes up. So these clouds are actually under-pressured relative to the ambient medium. You can calculate column densities of various ions in these fronts, and here we did that and compared it with some data from Bart Wacker for clouds in the galactic halo. This is the COS halos survey. So the black is the data, and it's plotted against the ratio of carbon-4 to oxygen-6 and silicon-4 to carbon-4. So here's the data, and in color you see various models. So our model is here, these cosmic ray fronts. There are actually a lot of points here for different parameters of the model, and they all look about the same. A time-dependent cooling flow model by Bob Benjamin works quite well. Collisional ionization equilibrium fails. These things are way out of equilibrium. Conductive interfaces, a couple of different models, are not too good. And I think it's fair to say that our model is competitive with the other best model. It's somewhat displaced from the data, but it's better than this and it's better than this. And we're now putting in heating, the effect of photons from the hot gas, and that seems to be moving this point a little bit to the right. So we're hopeful that this is consistent with observations. Okay, now, as I said, we wanted to test the effect of different cosmic ray treatments, and so let me take you briefly through a couple of them. So if there's a plasma process that damps the wave, then the cosmic rays stream at faster than the Alfvén speed because the cosmic ray excitation has to be stronger to overcome wave damping. And we're going to parameterize that by inserting a factor f in the Alfvén speed where f is greater than 1. But the heating rate is actually not going to change. In this extrinsic turbulence picture, where other sources of waves exist, there's a sort of composite streaming velocity, which is the Alfvén speed weighted by the relative frequencies of scattering by forward and backward going waves. And so if there are equal numbers of forward and backward going waves, so-called balanced turbulence, then this streaming velocity is 0. So in that case, the cosmic rays are just locked to the gas. And you can go through similar work, similar gyrations to what it took to derive the original theory and derive this modified cosmic ray energy equation with a reduced heating rate and a little bit of acceleration by forward and backward propagating waves. The pressure gradient force is unchanged. The heating rate is reduced. So let's see how this suite of models goes in global simulations of galactic winds. So this is work with Mateusz Ryskowski and Karen Yang that was published earlier this year. So we followed the galaxy formation herd and set up a gas disk in a dark matter halo and have a simple prescription for star formation and supernovae and cosmic ray production. And here on the left is what you get if the cosmic rays are frozen to the gas. So this is the extrinsic turbulence picture with 0 streaming relative to the gas. So there's this kind of puffed up gas layer and no wind. If you allow the cosmic rays to stream at the Alfvén speed, so the original classical hydrodynamics model, boom, you get this huge wind. So a striking difference. How does it affect, well, before we go into how that affects star formation, you have to ask if that puffed up gas layer is stable. And this is actually my current work to extend the Parker instability with cosmic rays streaming and heating, and all the indications are that it's a lot more unstable. So Evan Heinz, a new student, is working on this with me. So maybe it'll turn out that that picture on the left cannot be realized in a high-resolution simulation because of the Parker instability. But let's just take it at face value for the time being and look at a bunch of different models. Here on the left is star formation versus time with a number of different cosmic ray treatments. So the no wind picture that I showed you on the left of the previous slide is in blue. And you can see that there's a peak in star formation and then a drastic quenching. If we allow cosmic rays to stream at the Alfvén speed, a wind is launched. That was the picture on the right. The star formation rate again comes down, and we get this green line, not as low as the blue line, and here is that wind. So mass and solar masses per year versus time. And if we assume that cosmic rays are streaming faster than the Alfvén speed, so red, F equals 4, black, F equals 8, we get higher star formation peaks, some reduction, but not to the low levels as the other models. With time, reduction of the star formation rate, and we get a more intense wind. So what's happening here is that as we increase F, there's more efficient cosmic ray transport. The cosmic rays rise out of the galactic plane. The gas there is lower density. It's easier for the cosmic rays to escape and drive a wind, but they just leave the dense gas behind, and there's less of an effect on the star formation rate. So which of these models is the most accurate? So that's what we're currently working on. Okay, one more application, galaxy clusters. Where are the cosmic rays? So there was a prediction that the Fermi Gamma Ray Telescope would see diffuse gamma ray emission coming from clusters of galaxies, cosmic rays injected by an active galactic nucleus and by the galaxies themselves. But the limits on this diffuse source are very, very low. So where are these cosmic rays that are supposed to be there? So we looked at this whole cosmic ray streaming model under the conditions that we find in galaxy clusters, where the beta parameter, the ratio of magnetic to gas pressure, oops, this is upside down. This is supposed to be P gas over P magnetic, is very high. So sorry, galaxy clusters, in galaxy clusters, the magnetic field is relatively weak. The energy density in the thermal gas is relatively large. So beta in the center might be a few tens, and it generally falls with distance. And we're not sure exactly how it falls. So in a high beta plasma, the waves that cosmic rays excite are very strongly damped, absorbed by the ions, if they propagate at even a tiny angle to the ambient magnetic field. They beta to the 1/4, theta whole quantity squared. We estimated theta from a model of MHD turbulence in the cluster. So there's an intrinsic theta because the field lines that the cosmic rays propagate along are not completely straight. So without going into too much detail, we calculated a Landau damping rate that's proportional to the square root of beta. This drastically increases the streaming speed of cosmic rays and leads to a drastic reduction with time in the radio emission from the cluster. So we think that this may be a way of actually checking whether this model is right. And we just submitted this to monthly notices. Okay, so I hope, if nothing else, I've convinced you that cosmic rays really are a major ingredient in the energy and momentum balance of diffuse gas throughout the universe. And the interaction is collisionless, and it's mediated by gyroscale plasma waves. And this microscopic interaction drives behavior on macroscopic scales. It can determine whether the gas in a galaxy is stably or unstably stratified, whether clouds can be accelerated and eroded, whether a galactic wind is driven or the interstellar medium is just puffed up, and whether cosmic rays can be efficiently transported in galaxy clusters, and many more. So, thank you.
Thank you, Ellen. Any questions?
Can I take off my science fiction headset? Thank you. Okay.
So it's just a question on a detail. You show the star formation rate of this galaxy, right? And the effect of feedback from cosmic ray and supernovae only. So is this what size is this galaxy?
Oh, which galaxy? Oh, the simulation?
Yeah, the simulation.
Yeah. So you can actually see that. So these are. This is going to be, a Milky Way-like galaxy, an L-star galaxy. You can see the tens of kiloparsec disk and large halo.
So it's a bit worrying that in a starburst 150 solar masses per year, supernovae are doing very little.
Yeah. So the okay. So I can say a couple things. So one of the motivations for this type of study is that the numerical simulations, which include this parameterized star formation, if you take them at face value, they produce way too many stars. So that's the theoretical motivation. And to be honest, I've talked a lot with galaxy simulators. Do you think you really have the right star formation prescription? We don't understand star formation completely in our own galaxy, and they all consider this to be a robust problem, and that's the motivation for feedback of any kind.
Okay.
More questions?
So the Rosat, this all-sky map that you show, reminds me to the Fermi bubbles. And there is one of the theoretical models is that it could be that in the past we had some jet, like an AGN, with some precessions and rotation that will create that. So will this scenario of AGN model for the Milky Way fit with the scenario with the cosmic rays? I mean, do you envision some strong problems between these two theoretical models?
Yeah, interesting question. So I'm actually a co-author of a couple of papers on the Fermi bubbles as powered by a brief AGN phase of the galaxy. And I know that there are competing star formation models for the Fermi bubbles. So our models, as we envision, at least in our models of the Fermi bubbles, the entire bubble is a relativistic plasma with a tangled magnetic field. And the cosmic ray propagation in it is probably quite different from the cosmic ray propagation in an interstellar medium. Now, you can envision a sort of hybrid model where you had thermal plasma and cosmic rays injected by a jet. And that type of hybrid model, I don't think we or anyone else have really done it yet. But yeah, it's a very good question.
Thank you very much.
You gave us a very general description of the principles, which is very useful for people who don't know very much. Are you applying these ideas of the interaction of cosmic rays with the ISM mainly to the centers of galaxies, or to distributed star formation over whole disks, or to individual OB associations surrounded by their own expanding bubbles?
All of the above. So a few years ago, Josh Wiener and I, so Josh was a visiting student in my group before he became my postdoc, and we wrote a paper on, so if you look at the distribution of temperature in the ionized gas in the Milky Way with height above the galactic plane, this was a study done by Ron Reynolds a number of years ago, there's evidence for an extra heating mechanism with height. So most of the heating probably comes from UV radiation from hot stars, but there is evidence for supplemental heating. And we applied this VA.grad P cosmic ray heating, created a temperature profile. It actually fits the observations extremely well. So that was our first application of this. And I'm now working with Elena Dongia, who's a galactic dynamicist colleague of mine, and Chad Bustard, one of my grad students, on applying these ideas to the Large Magellanic Cloud. So I think it's actually very important to try to test this with local models to the extent that's possible, because so many assumptions go into it.
Thanks.
More questions? Okay, let's thank Ellen again, and don't forget there's science coffee.